Alright guys, I'm going to walk through a few examples here. So let's start here on this first page. On number 1, when it's asking for the given, it does this every single time. Now your given is just what you're starting with. So it says if you're starting with, meaning what you know that you need for an exact quantity is 34.8 moles of ammonia NH3. So if you want to call that nitrogen trihydride, you can. Now when it says where did that 3 MOL H2 over 2 MOL NH3 come from, you should have said from the balanced chemical equation, meaning the 3 is the coefficient in front of the hydrogen gas, and the 2 is the coefficient in front of the ammonia gas. Now down below it said double check to see if this, so 52.2 MOL of hydrogen gas is the correct answer. You know you need to go from this guy and go back. So you just take the same step and go back. So when I do it in reverse, I should get 34.8 moles of ammonia. Knowing that there are 3 moles of hydrogen gas for every 2 moles of ammonia, I will take 52.2 times 3 and divide it out here. I'm curious if I have a calculator tool. No, just rulers. Calc tool would be very handy. Alright, so I'm going to go 52.2 times 2, enter, divided by 3, enter, and I'm going to round that to 3 sig figs, and I actually get exactly 34.8, and MOL NH3 proves that I got exactly what I started with. Alright, so that first step just went one by one through it. Now they wanted you to look at this next balanced equation. And it tells you that there are 4 parts phosphorus to 5 parts oxygen gas to yield 2 parts diphosphorus pentoxide. So you are going to start, with your given quantity of 3.4 moles of O2. So if you have 3.4 MOL, and you can say of or don't say the of, either way is fine, O2. I know because that is technically on top. I need on the bottom of my first conversion factor to have MOL of O2. But what I'm going to is MOL of P2O5. So oxygen to P2O5 means that I have 5 moles of O2 to 2 moles P2O5. Alright, moles of O2 cross off. And I'm going to have 3.4 times 2 and divide it by 5. And I get 2 sig figs, so 1.4, my unit is MOL P2O5 or diphosphorus pentoxide. Again, 2 sig figs because that is what is in my given. How many moles of phosphorus are needed to react with? So now I am starting with 30.1 moles of O2 and I have to go 2 moles of phosphorus. So 30.1 MOL O2. Now to get to moles of phosphorus, I know I need moles of phosphorus on top, and I need moles of oxygen gas on bottom. So I go back to my equation, and I got in pink here, 5 for the oxygen, and for the phosphorus, it is a 4. So I'm just going to moles of phosphorus. That's what I am at. So I'm going to take 30.1 times 4, enter, divided by 5, enter, and I round my 24.08, I see on my calculator, to 2 sig figs, which gives me 24.1 moles of phosphorus, or 2.41 times 10 to the first. Alright, number 5, aluminum reacts with copper 2 chloride to make aluminum chloride and copper. Now this is one of the best examples for practicing for your quiz, because writing this balanced chemical equation is probably one of the more challenging parts when we're introducing this. So we're going to say copper 2 chloride, Cu, that means it's a 2 plus, Cl1 minus, remember crisscross, so the 2 comes down behind the chloride. Oh, I accidentally erased the whole thing. So it becomes CuCl2, reacts with aluminum. Aluminum is a metal, can exist just by itself, and it's going to react to make aluminum chloride. So basically this aluminum is going to what we call displace that copper, and then the copper is going to be by itself now. Again, also capable of being by itself. So we're going to balance this equation because there are 3 parts chloride and 2 parts chloride in this equation. So the lowest common multiple between 3 and 2 would be 6. So we have to put a 2 in front of the aluminum chloride and a 3 in front of the copper chloride. Because your aluminum now is a 2, you have to 2 in front. Your copper became a 3, so you have to put a 3 in front. So now this is your balanced chemical equation. Now your last step every single time should be to verify if there's anything that can be simplified, and you cannot divide 2, 3, 2, 3 by anything to simplify. So this is our balanced chemical equation. Now B says, given 6 mol of CuCl2, how many moles? So I'm going from 6 moles of copper chloride, 2 moles of aluminum chloride. So copper chloride to aluminum chloride, I'm going to use the molar ratio to relate them. So copper chloride goes on bottom, 3 mol CuCl2, 2 mol AlCl3 on top. Moles of copper chloride cross off, and I'm left in moles of aluminum chloride, which is what I needed to get to. So you're going to take 6 times 2, which is 12, divided by 3, and you're going to get 4 moles of aluminum chloride, and you have 1 sig fig to work with. Now, C, you're going to start with 4.5 mol Al, so aluminum chloride. To go to copper chloride, you're just going to switch those factors around. Now you're going to have 2 mol AlCl3 and 3 mol CuCl2 on top. Moles of aluminum chloride cross off, and we're left in moles of copper chloride, which is what we wanted to get to. So you'll take 4.5 times 3, so it's 8. 13.5 divided by 2, what is that, 6.75? Let's verify. 4.5 times 3 divided by 2, yes, 6.75, but I have to round that to 2 sig figs, giving me 6.8 mol. Again, the of, give or take, either's fine. CuCl2, though. You must tell me how much, what are you measuring in, and what is it? Those are a must. And to the proper number of sig figs. All right, 6, methane. So CH4, or carbon tetrahydride, and sulfur are going to react to produce carbon disulfide and hydrogen sulfide. I found this one was the one kids struggled with the most, but there is no prefix on that, so that tells you that that is an ionic compound. Also, hydrogen has a +1 charge and sulfide has a 2- charge, so it took 2 hydrogens. Often used to make cellophane, which is a plastic film cover. So let's balance it. This one came out a little tricky, but the thing you should remember is there's 1 carbon on the reactants and 1 carbon on the products, and there's 4 hydrogens and 2 hydrogens, so those will balance pretty easy. But because you have 8 sulfurs here and you have 2 and 1, you know sulfur is going to be your dicey one. So let's just start by getting rid of the odd number here by throwing a 2 out front. Okay, so then you have 4 and 8. So this side we need to get up to 8 sulfurs. Now the problem is going to be is if we change this one, we also change the hydrogens, and if we change the hydrogens, then we also change the carbons. So I think the easiest thing would be is to realize you're going to have to change both of them, but you want to do it as little as possible. 2 isn't enough, because if I change that to a 4, I'm still going to have 4, and then that'll be an 8 by itself, so I think that's too much. So my thought was then, well, let's try, wrong eraser again. This as a 4, still would get rid of that odd number, and then I'll have 4 sulfurs here. and I have 2 sulfurs there. Okay, and then what happens is because this hydrogen became an 8, I need to make this hydrogen 8, which meant I had to put a 2 in front, and then I have to put a 2 in front here, so then I have 2 carbons, 2 carbons. I have 8 hydrogens and 8 hydrogens, and I have 8 sulfurs and 8 sulfurs. So that is my balanced chemical equation. Erase a couple things here. Oh, it's really nice outside. I should go home. All right. Let's do a couple more. I'm going to finish this one, maybe do a couple more. Let's at least do one of this one. So calculate how many moles of, so we want to go to this when we're starting with this. All right, so we're going to start with 1.50 mol S8, and we want to use the molar ratio because we're just going to moles of one part. So we want to go from this guy to this one. Now notice, if your balanced chemical equation was not correct, you cannot do this. I didn't need to simplify, but remember, if you ended up with anything you can divide out in your coefficients, you need to do that. But I'm going to look for my sulfur. There is no coefficient, so that means I have 1 mole of sulfur in my balanced chemical equation and 2 moles of my carbon disulfide. All right, I want to encourage you to start saying carbon disulfide instead of saying CS2. Okay, I say it sometimes just because I know it's just adding a little extra challenge to things that already are challenging, but we need to get that repetition in our brains. All right, let's take 1.5 times 2, and it'll be 3, but because we are given 3 sig figs, it needs to be 3 sig figs. MOL CS2. All right, how many moles of H2S? So again, that is hydrogen sulfide because it is not a diatomic, or not a covalent molecule. Hydrogen is acting as an ion in this situation. So how many moles of this guy are produced given this information? So the fun part here is we can either use this or this. You can either start with 1.5 moles of the sulfur, or you can start with the 3.00 moles of carbon disulfide, because both are true to what we're trying to get with. So I think probably most of us would have probably started here. And the reason I would tend to start here as well is because we would have less rounding and it would be a more exact or precise number to work with. So I would tend to start with my original given as well. So how many moles of hydrogen sulfide? So I know based on my formula again, there is 1 mole of sulfur, and my hydrogen sulfide is what I'm looking at this time, and there are 4 moles of hydrogen sulfide. So I'm going to take 1.5 times 4 this time, and so this is going to come out to be 6, but again, it has to be 6.00 mol of H2S, or hydrogen sulfide. All right, so model 1 was to show you moles to moles of 2 different substances within a balanced chemical equation. So that would probably be your most likely summarization there, something along those lines. Now, model 2, you're going to go from moles to mass, but you have to go moles to moles of another substance with the molar ratio, which is this guy. So this is going from moles of ammonia to moles of hydrogen gas, and then to go from hydrogen gas moles to grams. Okay, so this is a 2-step. Same thing here. This came from a balanced chemical equation. Where did this come from? That came from the molar mass of that substance. Now, how much does 1 mole of hydrogen atom weigh? Why is the molar mass of hydrogen 2.02 grams per mole in the example above? Because 1 mole of a substance is not 1 atom. When we look at the periodic table, we know 1 mole of hydrogen, 1 mole of hydrogen is going to have a molar mass of 1.008 grams of hydrogen. Okay, but the molar mass of H2 is 2 hydrogens. Okay, it's because there are 2 hydrogens in H2. So you had to add that mass twice. All right, 105 grams of H2 is the correct answer. So you just do the back process. I'm going to advance to some of the more challenging problems here because I need to go home. All right. Let's look at 20 I did in class. I'll just quickly jot this one down. So how many moles of this when we're starting with this? So your given quantity, 3.4 grams of O2. You know you have to have mass on the bottom. So this time instead of just going moles to moles, you got to go grams to moles, then moles to moles. Okay, so in 1 mole of O2, you should know that there are 31.998 grams of O2 because it's oxygen times 2. Grams of O2 cross off, and I'm in moles of O2, but I want to get to moles of diphosphorus pentoxide. So we look at our balanced chemical equation and see 5 parts oxygen to 2 parts. So 5 moles of O2 to 2 moles of P2O5. So moles of O2 cross off. So you're going to take 3.4 divided by 31.998 and then times 2 and then divided by 5, and you're going to get 4.3 times 10 to the negative second moles of P2O5. Circle or box your final answer. Now 21 is another one where you have to write the balanced chemical equation. So we've got titanium 4 oxide. So if that is a 4 plus and oxygen has a 2 minus, it takes 2 oxygens. And it's saying this is being extracted. Well, no, so this is being extracted from. So this is what we're starting with, and we have to use chlorine and carbon to get there. So remember, anytime you have chlorine by itself, it has to be Cl2, and it's going to yield what we're extracting out of it, which is the titanium tetrachloride. And then carbon dioxide is also released during this extraction. So now to balance this chemical equation, we have 1 part titanium. It's the chlorides that are unbalanced here, so we just put a 2 out front, and it's balanced now. The molar mass of titanium dioxide is, I'm just going to look here, you got to take the 15.999 times 2 and then add 47.867 grams for your titanium, and it's going to result in 79.865 grams per mole of titanium dioxide. Now, how many moles of Cl2? So we're going to start here and go there. 1.25 grams of TiO2. My first conversion factor needs to have the mass on bottom. So 79.865 grams in 1 mole TiO2. Grams of TiO2 cross off, not the number, I accidentally drew a line through there. Now to get from titanium oxide to chlorine gas, I have to look at my molar ratio in my balanced chemical equation, and it is up here, so I've got nothing, so it's a 1. So 1 mole of titanium oxide, and I'm going to chlorine gas, which is a 2 moles of Cl2, not just Cl2. All right, so I'm going to take 1.25 divided by 79.865 and then times 2. Again, do in individual operations here. 1.25 divided by 79.865, enter, times 2, enter. And I'm going to get 3.13 times 10 to the negative second mol Cl2. How many moles of carbon are needed to react with 1.25 grams of titanium oxide? Same process. We're going to start again with 1.25 grams of titanium oxide. So this is just telling you how much carbon you're going to need. So this first step is going to be the same as what they wanted you to see, because you just have to get out of grams of titanium oxide. So that's there. Now you need to use the molar ratio that relates titanium oxide to carbon, though. So titanium oxide is still a 1, and carbon is also a 1. So 1 mole of titanium oxide and 1 mole of carbon. And we're going to take 1.25 divided by 79.865 again. And if you really feel it, you can take it times 1 and divide it by 1, but it's obviously not going to change your answer. Still, only use your given quantity for your sig figs. Must be touching with my paper here. 1.57. Ooh, am I too far off? All right, 1.57 times 10 to the negative second mol of carbon. All right, now this one, if you want to summarize this model, you were able to go from the mass of a substance within a balanced chemical equation to moles of that substance, and from that you could go from moles of that substance to moles of another substance in the balanced chemical equation by using the molar ratio. Now number 29 I thought was a good one as well. Same thing, but this time you're going to take it one step further. So we still define the molar mass of oxygen gas, and it's still going to be 31.998 grams per mole of O2. All right, but we also needed the molar mass of that P2O5 or diphosphorus pentoxide this time because you're going to use it. They really set the problems up well to scaffold this for you. So this one came out to be 141.943 grams per mole of P2O5. All right, so I want to go here. When I'm starting here, my balanced chemical equation is already given to me. So I'm going between these two guys, going from there to there. All right, start by writing out my given, just like always, 3.4 grams of oxygen. And in 1 mole of O2, I'm going to have 31.998 grams of O2. So my mass of O2 crosses off, and now I'm going to use the molar ratio to get from O2 to P2O5, and I know because of my balanced chemical equation, there are 5 moles of O2 for every 2 moles of diphosphorus pentoxide. That's an O, an ugly O. There we go. All right, that's 2 MOL. That's all really messy. I'm going to rewrite that. All right, so double check my grams of O2 cross off, moles of O2 cross off, and I'm in moles of P2O4. This is where I realize that I am not done because I wanted to go to grams. So the difference here from the last problem is just this. We are in grams. We're in moles of P2O5. We have to get to grams of P2O5. That's what it's asking for. So now what you're going to say is, well, if I have 1 mole of P2O5, I actually have 141.943 grams of diphosphorus pentoxide. My moles of P2O5 cross off, and I'm in grams of it like I wanted. So in your calculators, this time you're going to take 3.4. We're given 2 sig figs, divided by 31.998 times 2, divided by 5, times 141.943. And again, do these in single step operations. So that's going to give me a final answer of 6.0. And that's grams of diphosphorus pentoxide. All right. I think the rest are pretty similar. This one is the exact same thing, but you use that one instead. Grams of magnesium required, same thing. You're just going to start with this is your given and convert it to mass of magnesium, same process. This one here, number 31, you'd have to balance. Notice you have a 2 and a 3 here, so you're clearly wanting to get to 6 first. Okay, bam, and it cannot be simplified. All right, calculate the mass of N2 produced by the decomposition of 100 grams of this. So we want to get from 100.0 grams of NaN3 to the mass of N2, or nitrogen gas. So I need to get it out of mass first, and in 1 mole, NaN3. My molar mass for that substance would have been about 65.011 grams, I think. Double check me on that. All right, grams of that cross off. Now I have to go for moles of the sodium nitride, 2 moles of nitrogen gas, and we use the molar ratio. So this guy to this guy. So there are 2 moles of NaN3 for every 3 moles of nitrogen gas. And now my last step is to get out of moles of nitrogen gas and into mass. So I know in 1 mole of N2, you're just going to take the 14 grams on the periodic table for nitrogen times 2. I'm going to get 28.014 grams N2. I just took the exact values. Now in your calculator, you are going to type 100 divided by 65.011 times 3 divided by 2 times 28.0, does that say 14, I think? 014. Okay, and I get, with 4 sig figs, 68.64 grams of nitrogen gas, or 6.964 times 10 to the first. That's a G. All right, there are a few solutions for you. Hopefully the rest came out pretty simply here. This is the same process but with volume, and I really don't get into volume too terribly much, but it was really good for you to see that we can do stoich for volume of a gas at standard atmospheric temp and pressure. Now, the very last one, you just needed to write the exact values. So just make sure in this one you would say like 1 mole of something is going to be equal to 6.022 times 10 to the 23rd molecules of it. They wanted you to be specific. All right, there it is.